All right, so very good evening, guys. Very good evening, guys. Correct. Quickly, we will start a little 2 3 days of break in the sessions that we were taking, small sessions, very helpful. So, today, one such session when we talk about uh, quantum numbers of atomic structure, and there we talk about what is called as the address of the electron, right? So primarily, all of you know that there are total four quantum numbers. Quick recap I'll give you before I quickly bunch in each quantum number separately. So I will tell you there are total of four quantum numbers. Four quantum numbers actually means NLMS, principal, azimuthal, magnetic, and spin. Four quantum numbers. Then there's a principle called as Pauli's exclusion principle that talks about that the four quantum numbers cannot be the same for any electron in an atom. Means for an atom, all the electrons will have different set of quantum numbers. So basically, at least one quantum number will be different in each atom, in each electron, not in each atom, but in each electron. So it's four quantum numbers. Four, all four numbers cannot be same for both the electrons, for any two electrons per se, which we will talk about in this session itself. And therefore, the quantum numbers, or say the spectrum as well, is called as the fingerprint of the electron, or we can say the address of the electron. Because once I know the set of quantum numbers, I can locate the electron in an atom, where it is positioned, and what is the energy of that specific given electron. Right? A little network delay. Is it better now? Yes. Yes. All right. So now quickly we start with something which is called as quantum numbers. Now actually quantum numbers were actually brought in to discuss the address of the electron in an atom. Where the electron is positioned, its characteristics and all those things were brought in to discuss the progress. However, there are set of four quantum numbers. Four quantum numbers. And in four quantum numbers, the order is very important. What is important is order is important. And those four quantum numbers are number one, principal quantum number, which is called as n. Second one is called as azimuthal quantum number, which is called as L. Third is called as magnetic quantum number, which is called as M. And the last one, fourth one, is called as spin quantum number, and that is called as S. Spin quantum number. Right? So each one, the order is very important. NLMS. So the order that we get is NLMS. And when I talk about the set of four quantum numbers, let me here itself clarify that there is something which is called as Pauli's exclusion principle. Pauli's exclusion principle. which states that no two electrons in an atom, no two electrons in an atom have all four quantum numbers same. No two electrons can have all four quantum numbers same, which means that quantum numbers will be exclusive to any electron in the atom. Which means that quantum numbers will be exclusive, which means quantum numbers are exclusive, which means quantum numbers are exclusive to any electron in an atom, are exclusive to any electron in an atom, to any electron in an atom, right? Which means quantum numbers are exclusive. So that was given by Pauli's exclusion principle. Now here itself we need to discuss two more things, right? That is the first one, which is called as the Pauli's, not, oh, sorry, not the Pauli's one. The first one, which is called as the principal quantum number. Because that is how we start with principal quantum number bracket small m, right? The first point about it, what does it tell about? Number one, it tells about the shell number. It tells about the shell number to which the electron belongs to. So basically, principal quantum number tells me the shell. If I say in my childhood days, it tells about KLMN, the first, second, third, fourth shell. Or now when we talk about it's 1, 2, 3, 4, that is the shell number which principal quantum number talks about. That is, it talks about the shell number. It talks about the shell number, right? It tells about the shell number to which the electron belongs to. What next? So when I know the shell number, I very well know, when I say the shell number, I very well know that it tells about the velocity. It tells about the radius that way. It tells about the radius of the, it tells about the radius of the shell. It tells about the radius of the shell. It tells about the radius of the shell in which the electron is present. In which the electron is present. In which the electron is present. Third one, in which the electron is present. Third one, it tells about the velocity or the energy of the electron present in the orbit. Of the electron present in the orbit. So it talks about all these significant things. It tells about all these significant things about the radius of the shell in which the electron is present, radius of the shell in which the electron is present. It tells about the velocity, because since I know the radius, I know the shell number, I can very well bring out the velocity of the rotating electron. All right. And with this happening around, I always need to, okay, you may copy it first quickly. I always need to know that my n, the value of n could be 1, 2, 3, and so on. That is, my n belongs to natural numbers. N cannot be 0. 0th shell is nothing. The shell number, minimum shell number is 1. Minimum shell number is 1. Maximum shell number is infinity. So when we do numericals here in structure of atom, wherein electron jumps from 1 to infinity, so the maximum shell number that you always have is infinity. So my principal quantum number ranges between 1 to infinity. Principal quantum number. All right. This is done. Principal quantum number changes from 1 to infinity, and this gives you the shell number. The second that I have in the order is called as azimuthal quantum number, which is called as L. Before I talk about it much, what is L and how does it talk about? All I want to tell you here is that L ranges from 0 to n minus 1. 0 to n minus 1. I'll talk about what is L. That will be more helpful for you. It is about your orbital momentum, right? 0 to n minus 1, which means for n is equal to 1, where n is called as the principal quantum number or shell number, right? For n is equal to 1, comma, L has to be 0. For n is equal to 2, L has to be 0, L has to be 1. For n is equal to 3 and so on, whatever number you want to take, my L has to be 0, L has to be 1, L has to be 2, right? So this is something which talks about the shape of the orbital. I'll tell you why. L is equal to 0 corresponds to S. Corresponds to S. Right? L is equal to 0 again corresponds to S. Similarly, L is equal to 1 corresponds to P. L is equal to 0 corresponds to S again. Then L is equal to 1 corresponds to P. And then L is equal to 2 corresponds to D. Similarly, L is equal to 3. Say for example, for n equals to 4, L will be 0, L will be 1, L will be 2, and L will be 3. Why? Because my L has to be between 0 and n minus 1. Right? So for L is equal to 3, it corresponds to F. Quickly pen this down because it will be helpful. Quickly pen this down first. Quickly pen this down. Just pen it down quickly. Copied. Good one. Right? Now, the one thing which I told you, let us pen it down that as well. That azimuthal quantum number, or different names are there to it, or what do I say? Orbital angular momentum, orbital angular momentum, or subsidiary quantum number. Subsidiary. So there are three names to it: principal quantum number, then subsidiary quantum number, and orbital angular momentum. Because all these three are related to the shape of the orbital, and that is what my azimuthal quantum number gives. The L represents. L represents the shape of the orbital. L represents the shape of the orbital. It represents the shape of the orbital. How it tells about it? Quickly let us see. When I say for L is equal to, for N is equal to 1, summarizing that, for N is equal to 1, it corresponds to S. Which means that for first shell, it is only 1S. Only 1S. For second shell, it is gonna be 2S and 2P. How do I know this? Because for second shell, my L can be 0 or L can be 1. For 0, it is S. For 1, it is P. So for 2, it will be 1S and 1P. And therefore, for 2, it will be 2S and 2P. Similarly, for 3, it's gonna be 3S, 3P, and 3D. Similarly to 4, it's gonna be 4S, 4P, 4D, and 4. That is how we do it. That is how we do it. For 1, it is 1S. For 2, it is 2S and 2P. For 3, it's 3S, 3P, 3D. For 4, it's DF also. So 4F is this one. So that is how is given by azimuthal quantum number. These possible combinations are given by azimuthal quantum number. Are given by azimuthal quantum number. Right? So if somebody says why 2D is not possible, sir, why 2D is not possible, then my answer will be because for n is equal to 2, comma, L can be 0 and L can be 1. However, for D, L should be 2, which is not possible, when n which is not possible when n is equal to 2, because L varies from 0 to n minus 1. It will never be equal to n. It will never be equal to n. So that is about azimuthal quantum number, which talks about the shape of the orbital. Right? The third quantum number that I have with me is called as magnetic quantum number. M. Magnetic quantum number. Right? And it gives the information about, it talks about, it tells about the orientation, spatial orientation of the orbital, with respect to, with respect to with respect to the axis. Right? So magnetic quantum number M talks about the orientation to which axis, what is that? And then the value of M varies from minus L to L. The values of M varies from minus L to L. Say for example, if my L is equal to 0, M is equal to 0. But if my L is equal to 1, my M is equal to minus 1, 0 and 1. Similarly, if my L is equal to 2, my M is gonna be minus 2, minus 1, 0, 1 and 2. Correct? And so on. And since here M has one value, therefore L0 represents S, L1 represents P, L2 represents D. And therefore, when we say M equals to 0, it's a one value, so one box. For three values, there will be three boxes. For five values, there's going to be five boxes. Right? So that is how magnetic quantum, although it's a correlation, I should say it's a matter of sudden thing that has happened, coincidence per se, that the number of boxes that you draw, each box is called as orbital. Each square box from here or here or here, right? Each square box is called as orbital. Each square box is called as orbital. And therefore, you see, the number of, it is a matter of coincidence to be honest, but the number of orbitals is equal number of orbitals is equal to the number of magnetic quantum number values. Number of magnetic quantum number values. That is, the number of orbitals is equal to, and there is no rule to it, to be honest. It is just sort of a coincidence, but it is not a rule. right? It's a matter of that, okay, I'm making one box for S, and wow, even magnetic quantum number has only one value. Okay, for P, the magnetic quantum number has three values, -1, 0, and 1. So that way, right? And then here you see each box can accommodate two electrons, and that was told by the fourth one, which is called as spin quantum number, right? Which is called as S. Spin quantum number, which is called as S. And how do I define that? Sir, my spin quantum number is that each orbital can accommodate two electrons. Each orbital can accommodate total two electrons of opposite spins. Of opposite spins. Right? Two electrons of opposite spins means by default we say one is clockwise and the other one is anti-clockwise. And to represent clockwise rotation, we say spin value is plus half. Anti-clockwise, we say spin is equal to, right, minus 1 by 2. So if it is gonna be clockwise, we say plus 1 by 2. If it's anti-clockwise, it's say minus 1 by 2. So what happens is spin quantum number tells about that each orbital can accommodate two electrons of opposite spin, and the values are plus half and minus half. So this is about that spin quantum number talks about. This is about what spin quantum number talks about. So now as an example, I'll give you two examples. Say for example, if I am on fluorine, which is atomic number 9, 1s2, 2s2, 2p5. 1s2, 2s2, 2p5, which says, say for example in 1s2, S is one box, so two electrons. 2s is again one box, so two electrons. But P has three boxes, 1, 2, 3. And then in 5 electrons, 1, 2, 3, 4, and 5. So now therefore you see you are one electron short. You are one electron short. So now what happens is that sorry, there was a call in between. Now what I'm saying is what happens is 1s2, 2s2, 2p5 is what we did it. Electrons are filled singly first. Electrons are filled singly first, and then paired. Electrons are filled singly first and then paired. This is also called as Hund's rule of maximum multiplicity. Hund's rule of maximum. Okay, you may copy it first quickly. You may copy it first very quickly. Quickly, you may copy. Alright, so this is copied, which says Hund's rule of maximum multiplicity. That is, electrons are filled singly first and then paired, right? But when does this happen? When equal energy, or I'll take a separate class on all these rules also. When equal energy orbitals are available, comma, electrons are filled singly first, but we will talk about it in a separate class, no, not a problem. So for example, if I am say nitrogen, which is say atomic number 7, 1s2, 2s2, 2p3, 1s2, 2s2, 2p3. Now say for example, I have to put the quantum numbers. My question to all of you would be, write the set of quantum numbers, set of quantum numbers for an unpaired electron, in nitrogen, right? For any electron in nitrogen. Say for example, I talk about 1, 2 and 3, correct? Now for the middle element, middle electron, I have to write the 4 quantum numbers. So how do I do it, sir? I do it that n is equal to 2. How did I do that? It was a spin principal quantum number, which is my shell number. N is equal to 2. Since I am talking about P, my L will be equal to 1. Why? Because L is equal to 1 for P. L is equal to 1 for P. Similarly, NL, M is equal to minus 1, 0 and 1. It could be that order. I'm talking about the center, so M could be equal to 0. Why? Because M will have 3 values, minus 1, 0 and 1. Will have 3 values, minus 1, 0 and 1. And then the last, which is the fourth, since it's standing straight, so my S is actually equal to plus half. Right? N2, L1, M0, S plus half is the quantum numbers of the nitrogen electron. Any electron in the p orbit, right? So this is how you talk about, you discuss the quantum numbers in any atom and their significance. But guys, just one thing, in case you knew this, it's absolutely well. In case you do not know this, do not miss reading the NCRT, which is class 11, chapter 2, structure of atom. Very, very important topic, and it throws a lot of questions in some form: electronic configuration, size of the atom, any inorganic chemistry, P block, D block, all these quantum numbers play a very, very important role, right? So, correct. So, when I say quantum numbers, I have covered more than 90% of what is ever required when we say of quantum numbers. But yes, once we summarize chapters one by one, and there we talk about the question practice also. Correct? Correct? So that's it for this very small session. But please revise. The small sessions are more helpful in revision. So quickly do this as well. Take care, and we'll catch up soon for a very, very long and a session completing session chapter, but very soon. Do not miss quantum numbers. It gives you bare minimum one question straight, and maybe more than one question as an application to the inorganic chemistry. All right, fine guys. Take care and good evening. Bye bye.